Next on the agenda, section 4.4. So once we know some things about exponentials and logarithms, the next thing is to sort of put them to use in different equations. Always looking for new and exciting different types of equations to talk about and solve. Mathematician's dream is always a new equation, I guess. So that's what this section is all about. We'll go in order, alphabetical order, I guess. So we'll do exponential equations first. What's happening here, right, is the sort of generic form in some sense is you've got, b, kind of raised to the x equals some value. That's not totally true. That's a sort of a simplified version. But the idea here, right, is that your variables are up in the exponent, right, just like if you have an exponential function. And the first thing we're going to look at is a case when you have a common base value. So you could have some sort of equation where you can sort of get the form b raised to the m equals b raised to the n. So if you have exponentials on both sides of your equation and you can get them rewritten, or if they just sort of are initially presented with the same base value, 2 to the something equals 2 to the something, right? 6 to the something equals 6 to the something. Well, then it follows pretty quickly that, right, then it must be true that the actual exponents themselves are equal to each other. In some sense, you could think of this, in some sense, as sort of canceling out the two base values. You can also just sort of think of it a little bit more just sort of from a reasoning perspective, where if you have exponential functions, exponential graphs don't sort of double back on themselves in terms of the y values and give you repeated values. So if you have, right, 2 to the something equals 2 to the something else, there's only one particular exponent that will give you a particular value. So it must be the case that the powers themselves are equal to each other, which simplifies our lives a whole lot. Let me give you an example, right? We're obviously going to not necessarily just start with 2 to the x equals 2 to the y, and then you have x equals y. That's just too easy. So this is sort of more interesting if we have bases that don't quite sync up. So let's say you have something like 2 to the x plus 3 equals, we'll do something relatively simple, right? Let's say 4 to the x minus 1, right? So you say, okay, this is 2 to the something equals 4 to the something. So these are not the same base, right, which is sort of the principle that we're looking at. But like, there's a pretty simple connection between 2 and 4 as far as base values go, right? We're going to try to look to rewrite 4 to the x minus 1 as a power of 2, right? And so the way this works is you say, okay, well, 4 itself would be 2 squared, right? 2 to the 2 is 4. And so then you're replacing the 4 with 2 squared, and then that gets raised to the x minus 1. So what happens to us here is you're saying, okay, so this is like 2 squared raised to the x minus 1. And what happens to us then is if I do a power raised to another power, right, an exponent of an exponent, our exponent rules say that you're going to multiply those two things together. The most important thing when you do this, right, so 2 squared to the x minus 1 becomes 2 to the 2 times the quantity x minus 1. So you have to make sure that you multiply 2 to both of those individual terms. You don't need to necessarily do that in this step. We'll maybe save that and do that in a minute. And so what we kind of have here as a reference then is the exponent on the left, x plus 3, should sync up with and be equal to our exponent on the right, which is 2 times the quantity x minus 1. So again, make sure you sort of keep that x minus 1 in parentheses so that you can expand it. So we can think of this as like cancel the base, and what we get is x plus 3, the exponent from the left, is equal to this 2 times x minus 1 quantity from the right. From here, this is a relatively simple, just like linear equation. In theory, you could get all sorts of different stuff up in the powers, right? You could do quadratics or all sorts of wild things. we're not necessarily trying to go berserk with that. We'll just sort of stick with things that are relatively straightforward and not get too all over the place. So from here, we're just trying to sort of move our x's to one side, move our numbers to the other. So we'll do maybe a minus x over here. We'll sort of add this 2. And so it looks like what we're going to get is 5 is equal to x. And that should be our solution. In theory, you could kind of double check it. The only catch here is you're going to get kind of big powers, right? This would be if x is 5, this is 2 to the 5 plus 3 would be 2 to the 8, is I'm not sure what off the top of my head, would be equal to 4 to the 5 minus 1 would be equal to 4 to the 4. That's true, right? Because then if we sort of go back to this version of it, this would be 2 to the 8 equals 2 to the 2 times 4, which is obviously 2 to the 8. So it works out from the perspective of them both having the base value 2. So without necessarily having to go through the full motions of like, what is 2 to the 8, we can still answer this question and get a solution and feel pretty good about it. The trick here, and so where we can be a little bit clever, I guess is the nice way to think about it, is if we have bases that are a little bit less obvious, that they're actually coming from the same point. So you have to be a little bit more clever with the exponents that you're working with. So let's take something like maybe 9 to the like 4x equals 1 over 27 to the x plus 3. So at first glance, right, in some sense, obviously, 9 and 27 are related, but we have to think of these exclusively in terms of like powers, right? So like 9 times 3 is 27, but that's not an exponent, that's just multiplication. So we need to figure out a way to relate 9 and I guess in some sense not even 27, but 1 over 27. So we have a couple different things to do here. So what's the common base value that we could maybe relate these both to? What would these both be like powers of? So 9 would be like 3 squared. That's kind of the only option, right? Unless you're doing something a little bit unusual, like trying to relate it up to 81, and it would be the root of 81. That's not necessarily what we're after. 27, right? Regular 27 would be 3 cubed. So this would be 1 over 3 cubed, and then you'd say, okay, well, how do I get 1 over? That would be the same thing as using a negative power. So our kind of relationship here is, so 9 is 3 squared, 1 over 27 would be 3 to the negative 3, so 3 cubed is 27, negative 3 flips it down into the bottom. So I'm actually going to have to rewrite both sides of this. So the 9 I'm going to call 3 squared, and then that's sort of raised to the 4x. So that's equal to, so then we'll say over 27, right? 1 over 27 is 3 to the negative 3, and then that's raised to the x plus 3. So once I've cleaned it up and actually sort of done that change, then I have some pretty good stuff, right? I can sort of multiply these powers together. This is going to be an 8x, right? So this is going to equal 3 to the negative 3 times x plus 3. I'll do the same thing I just did. I'll kind of leave those powers unmultiplied on the right, and then what we'll do is take, right, 8x is going to be equal to negative 3 times x plus 3. And so that we can work with and that we can clean up. This is another just like relatively short linear equation, right? So negative 3x, this would be minus 9 equals 8x. So we're going to get some sort of semi-awkward fraction-y type value. That's fine. We're not necessarily guaranteed to hit a nice whole number like we did in the first one, especially if we start pulling, you know, some more awkward relationships here with our exponents. So let's add this 3x over. So this is going to be what? 11x on the left equals negative 9. So that means our x value itself would be negative 9 over 11. And again, there aren't really any restrictions here on our exponential values. We could do a check. We're starting to get sort of weirder and weirder values here, so it's not a check where you necessarily would go all the way through this and say, okay, 9 to the 4 times negative 9 over 11, right? I mean, that's going to be a negative 36 over 11. The 9, to the, what's this going to be, the 11th root of 9, then raised to the 36, but it's 1 over that. I mean, this is just a totally wild thing to be ending up with, right? So in any event, we're not going to have to necessarily run this all the way through to the point where we're actually trying to get sort of numbers to numbers. We can feel pretty good about getting pretty much any number here. We're not going to have any issues getting, a negative number, positive number, 0. All those things work in the powers. As long as our linear portion works out, then we should be good to go. So that's exponential equations when we can write the equations with a common base. So the next video we'll do it when we don't have a common base, because obviously that's not going to happen every time.